Okay, now let's see. Just get myself organized here. Do you see my screen? Yeah, okay, now I see it. So it should be fine. Okay, very good. So last time, we discussed the concept of 4 vectors. Recap. So we argued that, I argued, right? I define a 4 vector as any quantity whose components undergo the transformation V alpha goes to V alpha prime, which is lambda alpha prime beta V beta, when the coordinates transform in the same way. X alpha goes to X alpha prime, which is lambda alpha prime beta X beta. Right? So any quantity whose components transform this way, I define as a 4 vector. Right? To be more precisely, this is a contravariant 4 vector. And then I argued that essentially this is going to end up the same as the standard definitions of vectors that you're familiar with and used to. However, it's a much more general. I don't know if you've ever seen that before, right? This way of defining. Now, the other thing that I argue is that the most important thing to remember is that a vector belongs to a single point in space or in space-time. A vector belongs to a single point in space-time. Again, you don't see that in Euclidean spaces, which are flat. You can freely move a vector from one point to the other, and some. Sorry? Can you hear me? Is there any question? I heard somebody. Are you trying to say anything? Oh, okay. Now, you don't see that when the space-time is flat, but it's going to be quite crucial when we will discuss non-flat space-time, namely curved space-times. Right? Of course, when we do that, then we run into the problem of direction, which we will solve due time. We're not going to do it right now. There will be time to get it. There is enough new mathematical concepts right now that there's no point in putting everything I told you. I'm going to do whatever is needed. So the general way of thinking of that is that in a general space which is curved, I call this a manifold M, I choose a point, and then I can put the tangent space, basically taking a flat space which is tangent to that surface, the manifold M, right? So the point is called P, and the set of all vectors that go through P, tangent to the manifold at the point P, they form a vector space which is called TP. This is a tangent vector space. And it has everything that you know from your linear algebra, first year linear algebra course about vector spaces, right? You can multiply by a scalar, you can add, there is a zeros component, everything that you know and love, right? The important thing that for me, this is, I treat it as something which is completely abstract, okay? And I need that for the generalization. And the other thing that we discussed last time was the idea that when we change a basis, nothing really happens to the vector, right? I have a vector here. I draw it with a line. And I can think of the components of the vector in one basis and in another basis. Right? these are two different bases. And when I want to describe the vector in these two bases, I'm going to get different components. But the vector itself is not affected by the change of basis. The change of basis is something I use for myself, for my way of describing the world. Okay, that's again, it's an important thing to realize because no, these are things that I guess many of them may know that intuitively, but you know, just to clarify, this is really the way things are. And
Asaf, can I stop you for a question, please?
yes.
So if we're saying that a contravariant vector is transformed the opposite way than its basis vectors, right? Then why do we have the same transformation above for the vector and for the basis vector, if I understand it correctly?
I did not. That's a very subtle point here. I treat the set of basis vectors. It's a very, very tricky point. You're right? Because I can think of a vector as a component times a vector basis, right? Every vector A, right, I write as A mu, E mu. Remember the subtle notation that I used here. E mu is a basis vector. Now I'm looking at the transformation. Of course, there is a summation here, right? Mu equals 0 to 3. I basically wrote the vector as the component times the basis vector, right? Now I'm looking at the transformation of the set of basis vectors versus the transformation of the component of a vector. It's quite subtle, right? It looks very similar when I write it down, but A mu is the muth component, right? A1 is the one, let's say X component of the vector, and E1, right, is a vector, basically. Is a basis vector in the X direction or in the one direction.
Okay, why then it explains why what's written above is correct.
What do you mean explains? I didn't explain it, just basically I define it, right? This is my definition of a vector is here. By the way, I could not see who was asking because I don't see all of you at the same time. I don't know how to.
It's me.
What's your name?
Daniel.
Daniel, yes, the one. Again, my definition of a contravariant 4 vector is an abstract object that belongs to a point, P, right, whose components transform the same way as the coordinates transform under Lorentz transformation. That's my definition. That's how I want to define it. Okay, and then the rest, as I'm proving it to you, it's actually going to be identical to what you are familiar with from your from your intuition about what is a vector. Now, what I'm arguing is that the transformation law of the set of basis vectors is actually going to transform exactly the opposite. Excuse me for 1 second. I need to close the door and we open it. Okay. And then I argued, I actually showed you, right, that if I treat the vector as being an abstract entity, and I look at the transformation law of the set of basis vectors, right, given that the vector itself is unaffected by the transformation law, right, by transformation, because it's an arbitrary choice of coordinates, right, so I have V mu E mu, right, is V mu prime E mu prime, right, and V mu prime, I can write it down as V mu, sorry, let's move it. So it doesn't matter because I'm looking at component by component. Lambda mu prime, sorry, opposite. Lambda mu prime mu V mu E mu prime. Then we ended up that if you want to express the set of basis vectors in the new basis, we have to use the opposite Lorentz transformation. E mu prime is just lambda, which I write with the exchanging the upper and lower, mu prime mu, E mu. So the transformation law of the set of basis vectors is actually the opposite as the transformation law of the components of a vector. And the real reason why I stick on that is to show you that there is more than one way of defining this abstract notation, right? In fact, right, we can say that this set belongs to another abstract space, which is the dual space to the vector space TP. So somebody raised the word functional last time, and you're actually right. So if I think of a vector as some abstract entity which lives in some abstract space, right? A dual vector lives in another space, but this is an object that can take one of the objects from the vector space and turn it into a real number, right? So if we say that V belongs to TP, then omega belongs to TP star. This is the dual vector space. If you get confused, don't get too worried about that, right? Just think of it in, don't get nervous by the fact that we're talking about abstract entities. At the end of the day, we will use these to do calculations, and you see that you end up with doing the same calculations that you're used to. So just now understand it better. I hope you understand it better. Again, idea is that we have this tangent space, I don't know, TP, and any elements in this space is, V, and I can think of the dual space, TP star, and anything that lives here is a dual vector, or one form. And what I know is that when omega operates on a vector, on an element in the vector space V, that gives me some real number. And it does so in a linear way, right? So omega that acts on A, V plus B, W gives me A times omega that operates on V plus B times omega that operates on, which is the real number.
Hey, Asaf, can I ask a question?
Yeah.
So that's what little confused me, because we said it's like, let's say column vector is a contravariant vector and row vector is a covariant vector. But actually when we treat them exactly the same. We consider the same basis for the both and the same transformation and everything we did the same. So, but it wasn't supposed to be like this, right? Because if you say right now, they have completely different bases.
Right. You're going to show that in about half an hour, you understand exactly why you did it so far, why you did not see that so far. Okay? Before the end of this lecture, you will get an answer, full answer to that.
Okay, thanks.
Okay, and I gave you at the end the example of a gradient, right? D phi, which many of you might have thought of it so far as being a vector. But according to the rules, it is actually a covector, right? Just to make sure, right? Everything that belongs to the dual space is called a covariant vector. So elements of TP star are called covariant vectors. Covariant because they change as the coordinates. Contravariant because it's opposite to the coordinate. And another name is one-forms. That's part of a more general theory, which is called P-forms, which is actually quite fun. Maybe towards the end, I will say if you, I'll say if you're interested in it. You want to go deeper into the math. And then I argued, okay, and the element, and then, okay, another thing which is important, at the end of the day, we don't really need this decomposition into components in a given basis because of the fact that the basis vectors, when they act one on the other, they just give delta functions, which means that we can simply write omega that operates on V. This is just omega mu V. And that's the same as V acting on omega. This will be a definition of V acting on omega. Which of course belongs to all. Actually, it's not a definition. It's an equality. So elements of the dual vector can act on an element of the vector space to give us some real number, and the same we can think of an element of the vector space V that acts on an element of the dual vector space. Actually, this is a definition of how it would act to give us a real number. So they two live in different worlds. Right? They can interact with each other, but they don't belong to the same vector space. Right? And so I gave you some examples to make it easier for you to think. It's not 100%, but it's very close. So one was to think of column vectors versus row vectors, right? And then the operation of a row vector, omega, omega 1, omega n, and the column vector v would be v1, vn, right? And then omega that operates on v is going to be omega 1, omega n, v1, vn, using the usual rule of multiplying a row vector with a column vector, sum over I, omega I, yeah. Exactly what's written here, right? Note that I don't even bother writing the summation because it's clear that when I have one lower and one upper indices, then I sum over them. And another example is the gradients, d phi, which is d phi over dx mu theta. Right? So just a set of partial derivatives with respect to some space-time coordinate system. And then again, using the chain rule, right? We can write d phi over dx mu and dx mu prime. Let's say, right, you can just write it down as d phi over dx mu prime over dx mu. Sorry, the opposite. Right. The x mu over the x mu prime. So this is just the opposites, right? This is just lambda mu prime mu. Just lambda mu prime mu, d phi over the x mu. Right. So indeed it transforms like the opposite Lorentz factor, Lorentz transformation. Excuse me. Right. Which is what we expect essentially. And that leads to a shorten of notation, which again, I'm going to use a lot, even without paying attention. So d phi over dx mu is d mu phi. And another very common symbol is phi comma mu. This is a very common notation. And once you get used to it, you'll say that it's very, very natural. Now, when a gradient operates on a vector, what do you get? If I have a vector v mu, which is X mu over d lambda, let's say, and I have a gradient.
Tensor.
No, I just get a number. D mu phi, dx mu over d lambda. Just d phi over d lambda, just in the chain. Just an ordinary derivative function along the curve. This is the vector along the curve. It requires a little bit of thinking, but again, once you think of it, it gets quite natural. Normally, I want to define a vector which is tangent to a curve, right? So I have my space-time, regardless if it's flat or not. I put a curve on that space-time. Now I start to see, okay, I want to describe where I am along this curve, right? I just think I draw a line. And I just put some values along this line. Right, lambda equals 0, lambda equals 1, lambda equals 2. So if you want to know where I am, right, I'm here, right? I'm in lambda here. So I want to get the tangent vector to the curve, right? It's just going to be the x mu. V mu is just the x mu over the lambda. All right. Any more questions?
Yes. Can you explain again why dou x mu to dou x mu tag is the inverse Lorentz transformation?
Well, that's by definition, right? Because the Lorentz transformation just take us from x mu to x mu prime. So if you want to go from x mu prime to x mu, you must use the inverse transformation, which again, it's by itself a transformation. Right? We said that the Lorentz transformation just takes us from the unprimed from x to x prime. So if you want to go from x prime to x, you must use the inverse. That's all.
Okay.
Okay. Why did I spend all this time speaking about that? Any clue? Because now there is a very natural extension of this whole concept of vectors, and that's called tensors. So I'm sure you've heard the name, but now we do the definition, we do it properly. So really it's a generalization of the concept of a vector, right? So formally, when I look at the dual vector, I said that the dual vector is really a mapping from the vector to R, right? An element of TP prime is just a mapping of a vector of an element from the TP space to R, right? So what would be a generalization of that? And then I also said that, again, I can think of a vector as a mapping from an element in the dual space to R. So how can I generalize that?
A mapping from one vector field to another?
Simpler than that.
A mapping from one mapping to another mapping, maybe?
No, that's going to be mapping from one mapping to another mapping. It's a mapping of a mapping. It's going to be really confusing. I already managed to confuse you. Simple.
A mapping from more than one vector to R.
Thank you. Excellent, right? So formally, right, a tensor T, which is called a rank KL or type KL. A tensor T, we said of rank KL, or called type, you want KL, well, that's a definition, right, is a multi-linear map from a collection of K dual vectors and L vectors to R. Right? Multilinear means that it's linear in each component by itself, in each of the arguments. That's it, very simple, right? So, using this definition, when I say a 0, 0 tensor, what it is, what do I mean?
Scalar.
It's a scalar, right? 0, 0 tensor. Right? What is a 1, 0 tensor?
Vector?
This is a vector. What is a 0, 1 vector? The bit 0, 1 tensor?
Dual vector?
Dual vector. Cool, isn't it? What about the transformation law of tensors? Right. So basically, if I have a tensor of rank KL, right, the way I'm going to write it, it's going to be T, right? Let's write it here, right? Let's write it here. So if I have a KL tensor, it will be written as T mu1 mu k as upper indices and mu1 mu L. That's the way I'm going to write it. That is a KL tensor.
No, but it is opposite to what you written that K is dual vector. It's the dual vector index. So maybe it's
no. K takes K dual vectors and map them into R. So it's a vector. The same way as a vector takes one dual vector and maps it into R.
now I got it. Okay.
Okay. Right. T mu1. Now, if I want to make it the Lorentz transformation, the transformation of a tensor, so how would I do a transformation law for a tensor? Of a tensor. What's the transformation of a tensor? It's actually very simple. I transform each index by itself, right? So if I want to transform this T mu1 to mu k and mu1 to mu L to D mu1 prime mu k prime mu1 prime mu L prime, all right, it's going to be equal to what? So each upper index transforms as a vector. So I have lambda mu1 prime mu1, but then that works only for one index. So I need to have another one for the second index, lambda mu2 prime mu2, lambda mu k prime to mu k. And what about the lower L indices? What about now?
You make the inverse one?
Exactly, I'm going to use the inverse transformation. So it's going to be lambda mu1 prime mu1, lambda mu2 prime mu2, lambda mu L prime mu L times T mu1 mu k mu1 mu L. So each upper index gets transformed like a vector, and each lower index gets transformed like a covector or a dual vector. Right? Each upper index gets transformed like a vector. Each lower index is transformed like a dual vector. Pretty much straightforward, right? You have to agree. You don't have to agree. I hope you agree. Okay, example. I actually showed you a tensor already. I never said it's a tensor. What was this tensor?
The metrica?
Metric. Very good, right? So we have a very important, well, what rank is the tensor?
2, 0?
0, 2.
0, 2.
This is known as the metric tensor. Easy. 0 upper indices and 2 lower indices. It's a 0, 2 tensor. Right. 0 upper indices, 2 lower indices. Right. Now this is such an important tensor, right? Again, now we can think of this tensor as acting on 2 vectors, right? We said this tensor can act on 2 vectors and gives us a, what does it do when it acts on 2 vectors? What do we get? What do we get when we take the metric tensor and operate with it on 2 vectors?
ds, like the distance?
No, mathematically. The object that we get, what does it belong to? What kind of object is that?
Scalar.
It belongs to R, right? It's just a number. Right? The 0, 2 tensor, when it acts, remember a tensor, Frank KL, or 0, 2, is a multilinear mapping from a collection of K dual vectors. K here is 0, right? No upper indices, and L vectors, so 2 vectors, to R. So when I take this metric tensor and I operate it on 2 vectors, I get something which belongs to R, right? So in reality, this is eta mu nu, v mu, w nu, right? Now this is such an important operation that it has its own name. How do we call this name? You know it.
Inner product?
Exactly. This is the inner product. Okay. This is the inner product. Right. So because this is so important, it has its own name. It's called v dot w. It has its own symbol, sorry, right? Which is w dot v. The symmetry follows from the symmetry properties of eta, right? Eta just has non-zeros in the diagonal. Right? So this is really minus v0 w0 plus v1 vx. Wx plus vy, wy plus vz. 0, 1, 2, 3. Right? So this is the inner product. Just define the inner product. Okay, so I'm actually using the metric tensor to define the inner product. Right? Now, okay, very similar to what you've seen from Euclidean spaces. How do I call 2 vectors whose inner product, or other word is dot product? That's another name. So 2 vectors whose dot product is equal to 0. How do I call them?
Orthogonal?
Orthogonal, right? So 2 vectors is dot product equal to 0 or orthogonal. Now, of course, since a dot product is a scalar, it is invariant under a Lorentz transformation, right? So that means, for example, that if you choose a Cartesian set of basis vectors, these are orthogonal in one frame, they will remain orthogonal in any frame. Think of that for a second. What is the norm of a vector? How do I define the norm of a vector?
It's inner product with itself.
Exactly. This is the inner product of the vector with itself. Right, so v squared, right, is defined as eta mu mu, v mu, v mu, or v mu, v mu. Now here comes a small catch. Or maybe it will be easier for you to follow what I'm saying. You can write here rather than mu or write in mu. Doesn't matter, of course, because it's a dummy index anyway. Here is a catch, right? In Euclidean space, right, the norm of a vector can only be what?
Positive number
Sorry?
or 0.
Non-zero, right? Sorry, non-negative, right? And if the norm of a vector is 0, then the vector is 0, right? But what about here in Minkowski space?
It can be negative.
Can be negative. Can be
Because
negative.
of the
It can also be 0 without the vector itself being 0. So there is a terminology, right? So we say the following: if eta mu nu, v mu, v nu is
Asaf,
yeah.
why did you add v to the mu on the row above? This is the symbol for the norm.
V mu, you mean this line here?
I think it should be v squared. No, the most left.
Most left one.
Because I made a typo.
Oh, okay, thank you.
Well done. That's what happens when you speak and don't think. Okay. So if the norm of a vector, right, is smaller than 0, then we say that v mu is, does any of you have any idea?
Time-like?
Time-like, very good. Now if it is equal to 0, then what
Light-like.
Yeah, it's called light-like. Light-like. And another name is null. It's a null vector. And if it's greater than 0?
Space-like.
Very good. That's the standard terminology. And you'll see shortly why it's useful, right? So of course, the norm of a vector it's a scalar, so it must be Lorentz invariant. The norm of a vector is a scalar, meaning that it is Lorentz invariant. Right, Lorentz invariant, it doesn't change when you make a Lorentz transformation. right? So v prime squared, right, is eta prime mu prime u prime v mu prime v mu prime, right? Now I can make the transformation law for the vectors. So eta mu prime, lambda mu prime, let's say rho, lambda mu prime, let's say sigma, v rho v sigma. I did something here which is not trivial. I just changed the order. I changed the order here, right? Why am I allowed to do that?
Because they're all numbers.
Because I look at component by component. Okay, because I have summations here. Rho and sigma. Also a summation from here and mu and v prime. Okay. So I'm looking component by component. So when I do it like that, I've got no problem changing the order of elements in the physical. Right? But this is exactly the transformation law of eta. So I have an eta mu rho sigma. Sorry, v rho v sigma, which is just squared. To get used to the index, it gets really, really quick. There's no problem. Okay, so the scalar product, you know, in a similar way, right? So this is for the norm, but of course, if this work out for the scalar product of any two vectors, it's a scalar, so it's a concern. So that's one example. The second example of a tensor is the Kronecker delta function. Right? Another tensor, another example. Right. Kronecker delta. It's the only one that I'm writing mu on top of mu because it doesn't really matter. Right? What rank or type is this tensor?
1, 1.
1, 1. Very good. This is a 1, 1 tensor. And I assume you know it, right? The component of this tensor, delta mu nu, is equal to 1 if mu is equal to mu and 0 if otherwise. Another tensor, it's going to turn out to be quite useful, is the inverse of the metric, right? The inverse metric. So how do I write the inverse metric?
I guess the same with a lower upper index indices.
Very good, very good. Eta mu nu with upper indexes. Right. Again, of course, this is the type 2, 0 tensor. Right. Which is, of course, defined as the inverse of the metric. So the inverse of the metric meaning that eta mu nu, eta mu rho, how did I write down? Eta rho nu, eta mu nu is just delta mu rho. Now, in Minkowski space, right, how does the inverse metric elements look like?
The same as the metric.
Exactly the same as the metric, right? But be careful because this is only true in flat space in Cartesian coordinates, right? And if we go to curved spaces, it's not going to be so simple. And the other tensor that I want to introduce is the Levitzivita tensor. right? This is a 0, 4 tensor. Which is defined by epsilon mu nu rho sigma. I guess you know it, right? It's either +1 if mu nu rho sigma, it's an even permutation of 0, 1, 2, 3. It's a -1 if mu nu rho sigma is an odd permutation of 0, 1, 2, 3, and 0 otherwise. Right? Otherwise, meaning the two of them are equal. Right? You've seen that before, right? I'm not telling you anything new. Right? The Levitzivita, right? So what would be, you know, epsilon 0, 3, 2, 1?
-1.
-1, okay? I go 1, 2, and 3. -1, -1, -1. It's an odd. Add a -1. Okay. What can we do with tensors? Questions so far? No? Okay. Manipulating tensors. What can we do with tensors? So one thing which we can do with tensors is to raise or lower index. Raise or lower indexes. Right? Raising and lowering indexes. Right? So the norm was actually a good example of using a tensor, using the metric to lower indexes. Right? Basically, we use the metric and the inverse metric to raise and lower indexes. We use the metric and inverse metric to raise and lower indexes of the tensor. So, you know, let's say that I have a tensor T alpha, beta, and gamma, delta. Right? Then I can use the metric and inverse metric to, you know, raise or lower the indexes. For example, right, I can multiply it by eta inverse metric. Let's say, I'll do a little bit here. Mu gamma, right? That's going to be equal to what?
The same tensors, but all of them are upper indices?
No.
Ah,
No.
it's a summation. It's T alpha beta.
No. No, you're still not listening. I have eta, mu, gamma.
T alpha, beta, mu, and delta down.
Exactly. So there are indices that I did not touch, right? Alpha, beta, and delta, I don't touch them. So they stay where they are at the same location. So I start with an alpha, then a beta. Now eta was used to raise the index gamma. So I really sum over gamma here because it's only gamma that appears as an upper and a lower index. So I end up with a mu here. And again, delta is not touched. Note that what happened here, right? I just raised and lowered the index. I didn't shift it. Okay, again, and if you look carefully, you see that I always have the same number of indexes that are not dummy indexes as upper and lower indexes in both sides of the equation. And dummy indexes appear in one side of the equation. Okay, let's take another example. So I have my original tensor T alpha, beta, gamma, delta, and I'm going to use the metric, let's say eta, mu, alpha. What's that going to give me?
beta as the upper index, and the lower is mu gamma delta.
What will be the first index?
Beta.
No. What will be the first index?
Mu.
Mu. Is it going to be as an upper index or as a lower index?
Lower.
Lower index. Mu. What's going to be the second index?
Beta.
Is it going to be as an upper or as a lower?
Upper.
Upper. And the third index?
Gamma and delta lower.
Lower indexes. Okay, again, eta, the metric is just used to lower the index, and the location of the index does not change. Okay, again, let's say I have now T alpha, beta, gamma, delta, and let's do, I don't know, eta mu alpha, eta beta, eta rho gamma, eta sigma delta. What is that going to be equal to? What would be the first index?
Lower mu nu and upper rho sigma. Oh,
okay, the
something.
first is just the mu. It's a sigma. Right. The second is a nu as a lower. The third, what's going to be the third?
Sigma.
No.
Rho is the upper.
Upper. And the fourth?
Sigma.
Sigma as an upper or lower?
Upper.
Upper. Okay, you got the idea? So I can use the metric and the inverse metric. Are quite useful, among many other things, to raise and lower indexes in the tensors. Right? The raising and lowering does not change the position of the index relative to the other indexes. That's important. Okay? Because there's a lot of meaning. Right, and the dummy indices are in the same side, and when you compare the non-dummy indices on both sides, it's the same. So using the metric and the inverse, right? So example, right? The metric and the inverse metric are very useful to take vectors and turn them into what?
Dual vectors?
Dual vectors, right? So I can write down eta mu nu v nu is a what?
V mu with low index.
It's a lower index. Very good. And if I have omega nu eta mu nu, that is
Omega mu as upper index.
omega mu. Very good. So I can use the metric and the inverse to turn vectors into dual vectors and vice versa. Now I'm coming back to the question that you asked me, which I can formulate, right? Why I don't see, why I treat gradients as vectors and not as, why you never thought of gradients and other elements of the dual space as dual space objects, and you always thought of them as vectors. Why is that?
Because the metric is identity.
Exactly, because in Euclidean 3D or 2D Euclidean space, the metric is just 1, 1, 1, 1. So you couldn't see it. There was no way for you to see that there is something that is changing here. But of course, that was true for Euclidean space-time.
Nonetheless, in a deeper meaning, maybe they do not have the same basis, right?
Yeah,
Rho and
nobody actually showed it to you until now. Yes, they belong to different spaces. You just could not see it because in 3D flat space-time, they're really identical. But when it goes to 4D and Minkowski space, then you see that there is a difference. Okay, I promised you an answer before the end of this lecture, and you got it. Okay, I see that in my lecture notes I put some more comment on that. There are something deeper here. That's true. So, you know, the simple answer I gave you, right? In Minkowski space, you have this minus component, right? So omega mu would be minus omega 0 and then plus omega 1 plus omega 2 plus omega 3 in Minkowski space. I have this extra minus here, which didn't you could not see it before. Yeah, there is something which is deeper here, and that is that what's the easiest way to say? You don't really need the metric to define tensors in some basic sense. Tensors are objects that live by themselves. They don't need the metric. We really don't need it here because in this course, we're always going to use the metric. But on a more general abstract level, there is something deeper here. Because in principle, you can define a gradient without the use of a metric. But again, I think that takes us way too far from what we're actually going to do in this course. So forget about it. It's enough that you actually know what we're doing here. Okay, another thing which we can do with tensors is in what's called contraction. It's another operation on tensors, which it's an operation which takes a KL tensor and turns it into a K minus 1 L minus 1 tensor. It's an operation that takes KL tensor and turns it into K minus 1 L minus 1 tensor. Right? By simply summing over one upper index and one lower index. So if I have T nu rho sigma nu, right, I can sum. I have one index which is dummy here, so you can see this is the nu. We just ask mu rho sigma. Okay, so that's called a contraction. It's a well-defined tensor. The things to not forget is that we can only contract one upper and one lower index. We cannot contract two indices which are either two upper or two lower. That's not possible. And the order of the indices do matter. That's an important. Index, order, do vector.
Why we cannot contract two upper indexes?
It's meaningless.
Okay.
This is not, it's just meaningless.
Okay.
It's not a legal operation. Okay, so basically T nu rho sigma nu is not the same as T nu rho nu sigma. These are two different indexes, two different tensors. Okay, that's why you have to be, when you do these things, definitely for, you know, when you're starting doing it, and you have to do it slowly, do it carefully, but to be very, you know, precise and careful in what you do. Okay, it's not hard, but it requires a lot of, you know, small, you can easily get lost in the algebra there, you know. Don't try to do it very fast because you get lost. And just follow the rules. I mean, the rules are pretty straightforward. Okay, that's what I want to tell you now about tensors. We will come back to tensors, but not now. Now we had enough math, then we can continue to do physics, or maybe even we should say, start doing physics. Any questions about the math part? No. Okay. But now we're going back to physics. Maybe we should say I'm starting doing physics. We're starting by kinematics. So let's start by defining for velocity, acceleration, and forces. Okay, so kinematics meaning that we're interested in the motion of a particle, right? Now, okay, that's maybe it should be the starting point. Kinematics meaning that we're interested in describing the motion of a particle, right? Now, in Newtonian mechanics, normally, how do you describe the motion of a particle?
X is a function of t.
Exactly, right? We used to think in Newtonian mechanics as S as a function of t, right? As time evolved, the particle evolved. Can we do it here? No, because time is a coordinate, right? So we cannot really do it. But that's rather, what we have is what's called this concept of a world line. So it doesn't work, but t is a coordinate. So instead, we replace it with the concept of a world line. Normally, it's been drawn in 2D as all the spatial part in the x direction and time, or ct, to keep it with the same units, in the upper direction. And then we can speak of a world line of the particle. So this is the world line. Right? So basically it's a curve that describes the motion of a particle in space-time. Right? For example, right now, I'm just sitting, so I'm not going anywhere. So my world line just looks like that, like a space, like a straight line. If I was to walk, then my world line would be doing something. Okay? Easy. So how do I describe the motion of a particle along the world line? So again, I define some coordinate or some parameter that describes the world line. Remember, it's very similar to what I've already introduced, right? So I put some parameter along the world line, I can call it sigma, right? And then I can describe the coordinates as a function of this parameter along my world line, right? So x mu is x mu of sigma, right? Make sense? So for each value of sigma, I have the 4 coordinates, right? X mu. And that determines some point along this curve, along my world line or your world line or whatever objects you're interested in studying. Do we have any restriction on the choice of sigma? That can be basically everything, but there is obviously a very natural parameter to choose. What is that?
Proper time.
The proper time, very good, right? So a natural choice, go back to blue, right? A natural choice of parameter along the world line is tau. Right? So basically I describe my world line or any world line as x mu is x mu of tau. Okay, now we have a way of describing where I am. Now, how can I describe my velocity or my 4 velocity or any 4 velocity?
It's derivative with respect to this.
Exactly. Now it's going to be very simple. Everything else is going to follow. Now we're going to see this is the magic. After we work very hard on the math, everything else now is just going to come up like that. So we can define now like 4 velocity, right? U mu is just going to be definition. Too many lines here. All right, it's dx mu over d tau. That's all. You can immediately see this is a 4 vector, right? Because its component transform the same way as the coordinates on the Lorentz transformation, right? Now, again, as any other vector, u mu is defined only at a single point along the world line. Okay. Now the proper time, right? The tau. Remember we had this. The tau, delta tau squared was defined to be -1 over c squared at mu delta x mu delta x mu. We call that. So we can write it down as tau, just square root of dt squared minus dx squared over c squared. I don't really have to keep the c because at this stage, most textbooks will just put c equal to 1, right? So it's just dt times square root of 1 minus dx over dt squared over c squared. So it's just dt times square root of 1 minus beta squared. So if I use that in the definition of u mu, right, then we have u0. What is u0? What is x0?
CT, minus CT.
So yeah, very CT, not plus b. X was defined with the CT. CT divided by square root of 1 minus beta 0, right, dt. So it just c over square root of 1 minus beta squared, sorry, 0, just gamma times c. This is the zeros component of u. And the ith component of u, times dxi over square root of 1 minus beta squared dt. Just 1 over square root of 1 minus beta squared dxi over dt. Again, gamma times vi. Or if you want, gamma times beta I times c. Right? I think you've seen that, no? Now we got it out of, for nothing really. Just follow a few simple rules and you just get it for automatically. What is the norm of the four velocity? U squared, right? It's not the second component, it's the norm of the four velocity. Right, so again, the definition of that is u mu u mu. That's right, it's eta mu mu u mu u mu. Right, I made use of the metric to lower index. So eta mu nu dx mu over d tau dx mu over d tau. Why change the order? I just don't care. Right? You can simply write it down as it's a bit sloppy. Eta mu nu dx mu over d tau squared. But d tau squared, so it's written here as minus 1 over c squared eta mu nu dx mu dx mu. So this is simply minus c squared. So what's the, how would I call u? Mu? What type of vector is that?
Time-like?
It's a time-like, right? Any vector that describes the velocity of any massive object is always time-like. Okay? In order to be space-like, you need to be able to travel faster than the speed of light. And that's not possible. Right. What about the acceleration? You see everything is going to fall down into place for nothing really. How do I define the acceleration?
Take the derivative of u with respect to tau?
Yeah, exactly. So the for acceleration, right, a nu defined as d u mu over d tau. That's a definition. And the force, relativistic force, that acts on the massive particle. And just generalize Newton's second law. Right.
Multiply the acceleration by the mass.
M, a mu, exactly. Which is just m du mu over d tau. I don't need to do anything. So this is what replaces Newton's second law of motion, right? It gets, you know, basically everything you want, right? When the velocity is much smaller than c, right? Then we get back, you know, gamma becomes 1, right? And all the spatial components get you back to the regular Newton force. Right? There is no force. Then we get that du mu over d tau is equal to 0, right? which give us back Newton's first law, right? And what's the name of this constant m?
The rest mass.
This is the rest mass. It's just a constant here, which is called the rest mass of the particle. Quite easy, isn't it? Okay, there is one interesting feature which can get you confused. So let's go over it and see that there's nothing really here. In fact, the acceleration, the forward acceleration is perpendicular to the forward velocity. I'm going to show it to you. The forward acceleration is perpendicular to the forward velocity. Right? A mu, u mu, right, is eta mu nu, right? And I switch it. Let's try it. Okay, no, that's okay. E u mu over tau, and u u mu. Yeah, okay, that's fine. But I just wrote down a mu as du mu over the tau, and u mu I wrote as eta mu mu times u mu. But this I can write as 1/2 of d over the tau of eta mu nu u mu u mu. Right? You can take the derivative once of u mu and once of u mu. It doesn't matter. But inside the parenthesis, right, is just a constant, which is minus c squared. So this is 1/2 d over the tau of minus c squared. Since this is constant, then this is of course 0. I take the derivative. Okay. Does any of you have any clue what happens here? How can it be? It's actually very simple. Right, I just show you that the forward acceleration is always perpendicular to the forward velocity. But what it really means, right, is that there are only 3 independent equations of motion. That the fourth equation is, is determined once you set the 3 equations of motion. Newtonian mechanics is okay. Okay. Think of that. So they're independent. They are perpendicular. But that simply means that only 3 independent equations of motion.
You mean that the special are independent and the time is determined by them?
No, the fourth equation. Normally you take the 0th one. Right. That's all it means. But you can choose whatever you want. The fourth equation depends on the other 2. That's all. I'm just I'm mentioning it to you because you might do it. You should do it yourself, and you check out and you realize, hey, what's going on? How can it be the acceleration is perpendicular to the velocity? It can be because the fourth component of the acceleration, right? And fourth component of the velocity. Energy and momentum. This is for massive particles. So what would be the natural extension of the form momentum? Natural extension to the form velocity. Would be to define the form momentum. How am I going to define the form momentum?
Velocity multiplied the rest mass.
Exactly. P mu is just defined to be m u mu or m dx mu or eta. I told you. Once you do the math properly, then you do the physics and you just get it. 10 minutes, we derive all special relativity. You don't need to do anything more. Right. So again, what will be the norm of the form momentum?
Minus mc squared.
Yeah. I assume that's what you meant. Minus m squared c squared. Right, which you get free from here. What's the zeroth component of the form momentum?
Gamma MC.
Gamma MC. What's the ith component?
Gamma MV.
Right. Gamma, beta I, MC. Or if you want, gamma M, BI. Now we haven't really touched that so far, but we said that gamma is equal to square root of 1 minus beta squared in the denominator, right? So when V is much more than C, that means that beta is much more than 1. And what is gamma? That's a Taylor expansion. Is there anybody here who did not see Taylor expansion? No, huh? Awesome. So what's the expansion of square root 1 over square root of 1 minus beta square, where beta is very small?
1 plus beta over 2 or something.
Or something, yeah. 1 plus beta squared over 2. That's a Taylor, guys, and this you should know.
Oh, it's easy to done, but I don't always remember it.
Okay. Do remember these things, guys. Okay. So if we plug it in, right in here, then we get that P0, right? The zeroth component is gamma MC, so it would be MC, approximately, right? Plus 1/2 M V squared over C, right? Yeah. PI. What do we get for PI? Just a minute. There is no hidden things here in my question. It's a very simple question. What is pi in this limit? The ith component of the form momentum.
It's mv plus correction.
mv plus correction, which will be of the order of v cubed, right? So it's roughly mvi. It will be of the order of v over c squared, which you can neglect. So what is that? What do we call that?
Classical momentum.
This is the classical momentum. Right? It's an internal momentum. Now what do I do with the zeros term? So I multiply it by
C, and then you get the kinetic energy.
That's P0 times C. It's approximately mc squared plus 1/2 mv squared. Right? So what is this term?
Kinetic energy.
This is kinetic energy. Right? And what is this term?
Rest energy?
Exactly, right? This is a term that has units of energy, right? And that's what's called the rest mass energy. Right? Now, honestly, that's quite amazing, right? Because once you just follow these rules, this term was never known before Einstein, right? This was never known. Everything else was known. This was never known. Once you follow the rule, this term just popped out of the equation. Right? This gets right out the formalism. Once you follow the formalism, with the vector, you define a u, you define a p. Right? That's essentially everything we did, right? Just define a u, just define a p. Then it was just a matter of identifying what you're seeing. Just get right out of the equation.
So now my question is, how can we neglect the mc squared all the time? Classically, you just take the kinetic energy.
Right, because the masses, you're not changing the masses. Because classically, when you have a collision between particles, the mass of the incoming particles and the mass of the outgoing particles are the same. So the masses cancel out. Where are they not the same?
When there is a loss of energy?
When there is what?
When there is a loss of energy.
Not a loss of energy. When there is a change of the mass in the process. What processes have changed in masses?
Nuclear fusion.
Nuclear. Right, exactly. Nuclear processing. Right? That's how the sun works, essentially, right? Remember, there was in the 19th century debate, how long is the sun, right? You know the story? Yeah? No? There was a debate between the most famous physicist of the time, which was Lord Kelvin, and the most famous biologist of the time, which was Charles Darwin, right? And Kelvin could calculate how, using the chemical reactions that I think, he could calculate how long it would take the sun to consume the fuel and end up. And he concluded this would be a few hundreds of millions of years, I think, or maybe even less than that, a few tens of millions of years. I don't remember the details right now, right? And Darwin had got no clue in physics, but he knew about fossils at that time, and he could guess. And I think that he used, I think they developed the theory of glacier motion. by that time. And he realized that life on Earth must have been much longer than that. And life could not have existed without the sun. So he estimated that the sun must be much, much older than that. But of course, he had no way of proving that. And there was no known energy source to support that until Einstein came, right? That's how, that's in the heart of atomic bombs, right? The nuclear weapons, and this is the heart of all stars. This is how stars are making their energy. Right? From summing mass and turning it into energy. But the amazing thing for me, from a mathematical perspective, is that you get that, right, immediately right out of the equation. You basically do nothing. You just follow the rules. Just do basic definitions, and it just comes out like that, right? And then it's just a matter of identifying what you're seeing is something which has units of energy, so it's related to energy somehow. Okay, so the reason why this is energy is also why this four momentum vector is also called the energy momentum 4 vector. So P mu is also called the energy momentum 4 vector. Because of this reason. And I can also write down using right, p squared is just so minus m squared c squared, right? That p squared is just just minus p0 squared plus pi squared. So if I change the orders here, I get that p0, right, is just e over c. By definition, is just pi squared plus m squared c squared to the power 1/2. I think you've seen that in the first year. Yeah, you know this equation. Sum of momentum squared plus the m squared gives you the momentum, the energy. Assuming all the units of C are in the right place. Yeah, go back to your first year. Again, seeing how everything here just follows essentially for nothing. Okay, there is slight difference about massless particles. I'll comment on that next lecture, and then we'll do another thing, and then that will be enough for us to study special relativity. Any questions? Okay, so as I promised, I'm going to post the first problem set on the web. If you don't have access to the web, then send me an email. I can give it to you. Okay, then you have all Passover to look it through, read it, and enjoy it, and make sure that things are very clear in your mind. There is a reason why you spend so much time explaining all these subtleties about vectors and tensors, because as you can imagine, how I should say, in a few weeks' time, you're going to be missing a lot these nice and simple matrices, the eta mu, which things will get much more complicated. I don't want to threaten you or anything, right? It's going to be much more fun, but you're seeing where it's heading. It's kind of a lot of fun around here. But once you get the math, then the amazing thing that the physics just go down like there's no real other way. All right. Questions, comments?
You said about the inverse metric in a curved space that it wasn't the same as the metric. That's also correct for the other inverses. Obviously, that's
what do you mean, inverse of what?
Of the Lorentz transformation.
It's a different thing, but yeah. It's an entity, but essentially, yes. I'm looking at Lorentz transformation is a transformation. You know that pay careful attention, right? I write it as a matrix, and the same way that I write the metric as a matrix, but these are completely different objects.
Yes, I know.
Right, the metric is a tensor. The real name is the metric tensor. It's a 0-2 tensor. That's the real name. Okay, so although it's written as a matrix, I keep on writing it as a matrix. But you know, the correct way to think of it, right? It's an object that have life of its own. The same way, if I can think as a vector as an object in a vector space, it has life of its own. I will describe it by a set of numbers, right? But it's my way of describing it. The way I really care about is in order for some object to be rightfully called a vector is how it is being transformed.
Okay.
Okay. So I know it's very confusing in the beginning, to be honest. I've been there myself. But that's why I'm trying to go through in detail all the areas that, all the points that I think can be quite confusing. But again, at the end of the day, I think when you read it and you think, and you got access to my lecture notes, so you can read them. I hope you do that. You know, just at the end of the day, you see that you just have to be like that. And indeed, when you do the math properly, then doing the physics is just like that. You know, just, you know, what did we do with the physics? Essentially nothing. I defined the for velocity, I defined the for acceleration, I defined the for force, and voila, I got the E equal mc squared. For nothing. Sorry, I also defined the for momentum. Right? And I got all the equations that you derived. I don't know, you worked for half of the semester deriving these equations in the first year. I just got them immediately out of the math. Right? Okay, have a good weekend. Think of that. We'll meet again on Sunday before the holiday. If you have any questions, you can ask me then. And then we will basically complete the discussion about special relativity. And then after the Passover, we'll start doing generalizing things. Okay? All right. So have a good weekend.
Thanks. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye.
Morning.
Hi.
By the way, how?
Asaf,
Yes.
do you know